Hello everyone, this is Jiayi Xu. I'm glad to present our work entitled Reinforcement Learning for Load-Balanced Parallel Particle Tracing. Particle tracing is one of fundamental techniques for flow visualization and analysis. By tracing particles' movements in vector fields, we can generate visualizations such as streamlines, path lines, and FTLE. A large-scale vector field and the particles are partitioned and distributed among evolving processors for parallel particle tracing. Challenges include imbalanced workloads among processors and high communication costs. Also, the processor's workloads and the communication costs dynamically change during the tracing. We propose the work donation technique. The core idea is that overloaded processors donate their work to low workload processors with minimized communication costs, so that processors gradually have balanced workloads. Work donation is a model-based reinforcement learning technique. We establish cost estimation models to estimate and predict future computation and communication costs. Reinforcement learning agents make work donation decisions based on the cost estimation to balance workloads and minimize the total execution time. Next, we present each component in the reinforcement learning. The current state of agents is corresponding to the current assignment of data blocks to processors, indicating which processor a data block belongs to. Agents can take actions to migrate data blocks across processors to change the state. Based on the policy function given the current state, agents will evaluate and decide on block movement actions in a stochastic manner. During the decision-making phase, the input features are workloads of involving processors and estimated communication costs of possible data movements, which are estimated by cost estimation models demonstrated later. A policy function maps the input features to probabilities of agents' actions nonlinearly, whereas processors with lower workloads have higher probabilities to receive data blocks. The policy function has trainable importance weights of the input features. Each agent samples an action based on the probabilities and makes the corresponding data movement. A reward is computed to assess the reduction of the execution time after actions have been taken. Because the execution time can only be obtained after the parallel program completes, to make the training more efficient, we leverage cost estimation models to predict and estimate the future execution time. The reward will then be used to update the parameters of the policy function using a policy gradient-based approach to increase the probabilities of actions with positive rewards. Please see details of the update of parameters in our paper. In the following, we present two cost estimation models used to predict particle advection computation time and communication time. To estimate the advection time of a new particle colored in red within a data block, previous researchers usually used the average time of all those black particles that have already been traced within this data block. In our study, we take the advantage of the similarity between particles' trajectories. Due to the data continuity in space and time, the green particles with similar trajectories usually also have similar advection time within the data block. To retrieve particles with similar trajectories efficiently, rather than storing and comparing full trajectories, we record and match particles accessed data blocks with much lower overhead. The particles with the same accessed data blocks colored in dark gray are retrieved for the estimation. The model order represents how many accessed data blocks of each particle are used for the matching. Higher model order usually has lower estimation errors and higher overhead. We also organize particles' trajectories using a tree data structure called trajectories tree to improve the matching efficiency. Please see details in our paper. To estimate the data transfer time of blocks and particles, we utilize a linear transfer cost model, where the time cost of transferring a data entity is proportional to the number of the entity plus a fixed starting latency. The coefficients of the linear model can be computed by the least squares method based on historical data transfer. We evaluate our method on 3 datasets, NAC 5000, Ocean, and Isabelle, and generate streamlines, path and FTLE visualizations, respectively. We first evaluate the high-order workload estimation model for the advection time estimation. The horizontal axis encodes the model order, and the vertical axis encodes the estimation error. The existing baseline method is the zeroth order model. Compared with the baseline, our high-order model can achieve 1/2 to 1/3 errors for different datasets. We evaluate the execution performance by compared with the state-of-the-art dynamic load balancing approach as a baseline. The baseline is colored in blue, and our method is colored in orange. The horizontal axis encodes how many processes are used. In the 3 columns, the vertical axis encodes 3 corresponding metrics, including total execution time, load imbalance, and I/O and communication costs, respectively. When 1024 processes are used, our method has 2.33x, 3.98x, and 36.93x speedup over the baseline across the 3 datasets. The reason of the performance improvement is that our method can attain both lower workload imbalance and lower communication costs than the baseline. We break down the execution performance of our method in detail when 128 processes are used. The horizontal axis is the execution time, and each row in the vertical axis represents 1 process. We profile the process's activities, including local computation, I/O and communication, and busy waiting. For NAC 5000 and Isabelle, each process has a similar aggregated active time, indicating our method balanced workloads among processes effectively. Next, we analyze why processes have a long busy waiting time for Ocean data. We plot the dynamic assignment of data blocks to processes on the Ocean data, where the horizontal axis represents blocks, and the vertical axis represents processes. Each black dot represents the block of the column is assigned to the process of the row. The workloads of processes are juxtaposed with the block assignment. At the early stage, initial workloads of processes were not balanced, and the initial block assignment presents the round-robin assignment pattern. Our method gradually balanced the processes' workloads by work donations among processes in the middle stage. At the later stage, only a few blocks had particles, making just a few processes had advection computations, and other processes remain in busy waiting. Now I have come to the conclusion of this presentation. We exploited the benefits of using reinforcement learning-based optimization to address a dynamic workload balancing and communication cost reduction problem for parallel flow visualization and analysis. Results demonstrate that our work donation technique can minimize the total execution time and outperform the state-of-the-art dynamic load balancing method in terms of parallel efficiency, load balance, and the costs of I/O and communication. Thank you for listening and thank our funding providers. I would like to take a few questions.